This video is about solving separable differential equations. First, we'll talk about what makes a differential equation separable, and then we'll discuss how to solve them, and we'll do an example. So if a differential equation can be written like this, we've got a first order differential equation, and you have the derivative of your dependent variable with respect to the independent variable is equal to a function of one variable times a function of the other. If the differential equation can be written in this form, then we say that it's a separable differential equation. Because if it can be written in this form, basically the idea is we can get all the y's on one side and all the x's on the other, and then we can just anti-differentiate both sides with respect to whatever variable happens to be there. Now, if I'm doing that, if I want to do that, the first thing I need to do is I'll multiply by dx on both sides. So then on this side, I'll have dy dx times dx, and on this side, I still have that product times dx over here. Now, it's very tempting to think of this like a fraction, and we often treat this like a fraction. Now, technically, we shouldn't think of it that way because this is a function. You've got the derivative of y with respect to x, and you're multiplying it by dx. So technically, these don't cancel out. There's not a 2 in the denominator that you're canceling with a 2 over here. That's not what's happening. But by definition, the differential of y is the derivative of y with respect to x times dx. So when you multiply this guy by dx, you actually do get dy. So you multiply by dx, and it's kind of like it's canceling, but technically it's not canceling, but it's gone now. And now you've got a dy over here. And then on the right-hand side, you've got this. Now I've already got all my x's on this side, and I've got a y over here, and then I've got this g of y over here. To get rid of this g of y, since it's multiplying everything else, we have to divide by it. So if we divide both sides by g of y, I have dy divided by g of y on this side equals f of x times dx times g of y divided by g of y. So the g of y is gone, and we get this. So through multiplication and division, you are able to get all the y's on one side and all of the x's on the other. If you can do that, if the equation can be written this way, so all the y's are on one side and all the x's are on the other, it's separable. Now, one other thing that I will point out to you is that you have to have dy times a function of y here, and dx times a function of x. This isn't going to work if your dy is in the denominator, or if you have like plus dy or minus dx. It has to be multiplying each other. In the same way that you would have an integrand multiplying dy, or an integrand multiplying dx in an integral. Okay, so you've got a function of y times dy here equals a function of x times dx. If you want to solve this, you anti-differentiate both sides with respect to the variable that's there. You can take antiderivative on this side with respect to y and the antiderivative on that side with respect to x, and then you're going to get some relation. Now, I want to write capital G of y, but that's not technically the notation that we would use. I'm just going to use h of y. You're just going to get a function of y over here plus a constant of integration. And then you're going to get a function of x over here plus a different constant of integration. If I take this c1 and I subtract it from both sides, I get c2 minus c1. Well, that's just a different constant. Since that always happens, you always end up with a constant of integration on this side, another one on this side, we usually just write a plus c on the right and let that c take care of both c's. So normally we skip these two steps. But that's it. Then you're done. Then that's an implicit solution. So let's just overview the method again. If the differential equation can be written this way, so you've got a product of your independent variable, a function of your independent variable, and a function of your dependent variable. The first thing you do is you just do what's called separating the variables. So you get all of your x's on one side and y's on the other if those happen to be your variables. Then you anti-differentiate both sides with respect to the variable that is on that side. Now there are some details about why that works the way it does. You can actually think of this as a U-substitution where U is equal to Y of X. You're actually anti-differentiating both sides with respect to X. But in practice, all you do is just take the antiderivative with respect to Y and the antiderivative with respect to X, and then you're done. So you do that, and then when you're finished, you've got an implicit solution. So it's really a two-step process. Separate the variables and anti-differentiate. Now you've got an implicit solution. And then if possible, at this point, you might solve for your dependent variable, in this case y, to get an explicit solution. Sometimes that's not possible though. Okay, let's do an example. Or actually, let's look at a few examples and see if we can't pick out the separable equations from those that aren't separable. So here's the question. And remember what our goal is. We're just trying to find a function or a relation that satisfies the differential equation. It's always about finding a solution. And then in this section, in this lesson, we are finding our sorry, I got distracted when I was looking for those equations that I wrote down earlier. In this lesson, we're learning how to solve separable equations. Okay. Because that's what most of this chapter is going to be about. We're going to learn all these different methods for solving different types of first order equations. The first method is separable equations. Question is this separable? If I get dy dx by itself, can I factor the other side? Well, let's take this guy and rearrange it. I'll subtract xy from both sides. Is that a function of x times a function of y? If you said no, you're absolutely right. So this is not separable. Because this is not some function of x times some function of y. And I can't make it a function of x times a function of y. What about this guy? I hope you said yes. Because it turns out that one is separable. It's just kind of hidden. You've got an exponential here, and you might be tempted to think that you can't split this up. But remember how exponents work. If you have x to some power times x to a different power, you just add the exponents. And that's going to be true for any base. That could be a base 2 instead of a base x. So if I have e to this power plus, or e to the 2x plus 3y, excuse me, well, I can separate that into an e to the 2x times an e to the 3y. It's just this rule backwards. So I've got a function of x times a function of y, so that is definitely separable. And then what about this last guy? Is it separable? It looks to me that like it's not, but let's do a little algebra. I've got 1 plus t times x, all divided by t squared minus x. Okay. Can I factor this? Actually, I think I can. Look, I've got an x here and an x there. So I can think of that as 1 plus t over t squared minus 1 times x. Distribute, and you'll see you get the same thing. This fraction times x gives me this, because that's an x over 1, remember? And x times negative 1 gives me that. So I've got a function of x times a function of t. Yeah, that's separable. But notice that this guy wasn't. You move all the x's and y's to one side, you've got that first derivative by itself. It cannot be factored. Another way to determine if something is separable is just to try to get all the y's on one side and all the x's on the other. You can multiply by dx, but that dy plus x dy, or xy that would be left, x would be an xy dx, like you would never be able to get a function of y times dy equals a function of x times dx. So yeah, that's not separable. So this is the easiest rule to check. Just to get that derivative by itself. If you can't write it as a product, it's not separable. Okay, so let's solve a differential equation, a separable differential equation. Got lots of them. Here's one. Let's say we have dy over dx equals x squared divided by the square root of y, and let's put a coefficient of natural log of y over e to the x cubed over here. The question is this a separable differential equation? Well, one way to test it is to multiply by the reciprocal of this, and then see if we can factor it as a function of x times a function of y. So I will get that dy dx by itself. Those guys reduce, and now we've got dy dx equals x squared times e to the x cubed divided by the square root of y times natural log of y. Yeah, that's definitely separable. That's a function of x times 1 over a function of y. So that's a separable differential equation. Now, remember, the way we solve these is we get all the x's on one side and all the y's on the other. In order to get rid of this dx down here, I'm going to multiply both sides by dx. That's where we're going to have that almost cancellation thing that happens. It's not quite cancellation, but that's how we define differentials. So those are gone. And I want that y expression on this side with the y, so I'll multiply both sides by the square root of y times natural log of y as well. All right, so we've got square root of y, which I think I'll rewrite as y to the 1/2 times natural log of y dy equals x squared e to the x cubed times dx. So what did we do? We verify that the dE is separable. Then we separated the variables. Usually involves a lot of multiplication and division. Sometimes addition and subtraction, but usually that step only is necessary to get all the terms on one side. And then you just anti-differentiate both sides with respect to whatever variable's there. So we're going to take the antiderivative on the left. This is all going to be with respect to y. And we'll take an antiderivative on the right. That's going to give us a function of x. Okay, so now I'm here and I'm looking at this and I ask myself, do my basic rules apply? And I say, no, I don't have a basic rule for that. Look at my sheet. It's a product. It's a natural log of y times a y to the 1/2. Do you see anything like that over here? No, it's not on the sheet. So then if basic rules don't apply, I always ask myself next, what about U-substitution? Will U-substitution work here? No, unfortunately it won't. The only inside function is maybe a y, but if I let u equal y, it's just going to change all the y's into u's, and it's not really going to help us at all. So yeah, we have to go to integration by parts. Always check basic rules first. If basic rules don't work, then try U-substitution. If U-substitution doesn't work, then try integration by parts. And we're going to do integration by parts here. Now remember, when you use integration by parts, that when you look at your integrand, if there's a natural log in it, that is your U. If there's an inverse trig function, that is your U. Otherwise, most of the time it's a polynomial. But this time we've got a natural log, so I'm going to let U be the natural log of y. Then everything else is dv. So dv is y to the 1/2 times dy. In order to use integration by parts, we need to compute du and v. So we're going to differentiate to get u, and we're going to anti-differentiate to get v. The derivative of natural log of y is 1 over y, and du is that derivative times dy. The antiderivative of y to the 1/2 comes from adding 1 to the exponent. 1/2 plus 1 is 3/2, and then you divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Then according to the integration by parts formula, you just go across here and then across there. It's u times v. The integral of u dv is u times v minus the integral of v times du. Now be very careful here. A lot of students will just take the antiderivative of this guy and that guy and multiply them. They'll use the power rule for this and multiply it by a natural log of the absolute value of y. Don't do it. You've got to simplify that first. There is no product rule for antiderivatives. So you've got to simplify. You can think of that as a y to the 1st in the denominator. You can think of that as a y to the 3/2 in the numerator. So you would just subtract this exponent minus this exponent. And you're going to end up with 3/2 minus 1 is 1/2. And I'll pull out the 2/3. After I've done my algebra, say, do I have a rule for that? I sure do. It's just a power rule. So we add 1 to the exponent, and then divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. And then typically we would also have a plus c over here. But I'm just going to let the c on the right-hand side absorb the c from the left-hand side. So we'll have 2/3 y to the 3/2 times natural log of y minus 4/9 y to the 3/2 equals that function of x that we're going to get on the right-hand side. Okay, so that is our left-hand side. On the right, we ask ourselves, do we have a basic rule for that? And we don't, because it's a product. And then the next thing we say is, can I use U-substitution? And it turns out I can. Now remember how U-substitution works. Whenever you're using U-substitution, you're looking for a function nested inside another function. Looking for that composition of functions, an inside function and an outside function. So you're looking for parentheses, square roots, radicals of any kind. If there are exponential functions, the inside function is usually in the exponent. If there are logarithmic functions or trig functions, the inside function is usually what's inside the trig function or inside the logarithm. We've got an exponential function here. And it doesn't have an x inside, it has an x cubed inside. So that tells me this is a good candidate for U-substitution. Now we're never actually sure it's going to work until we do a little bit of computation. And most people do this in their head by the time they get to differential equations, and that's great and that's fine. Say, okay, I'm going to choose u equals x cubed. If I compute du, which is the derivative times dx, the question is that up there somewhere? If this is up there somewhere, U-substitution is going to work. If it's not up there somewhere, U-substitution may not work, or you might have to be really fancy with your U-substitution to get everything written in terms of U. But most of the time, I'm just looking at this and I'm comparing it to this, and I'm saying, is this a factor in my integrand? And don't worry about the constant. It's really just a constant multiple of this. Question is there an x squared dx up there? And there is. There's an x squared dx up there. So that means this is going to be a good candidate for U substitution. So this is going to be my u, that's du. The integrand has an x squared dx in it, so I'll take this equation and I'll solve for x squared dx by dividing both sides by 3 or multiplying by 1/3, same thing. And then we can look at our integral again. This is e to the x cubed times x squared dx. In terms of u, well, this is e to the u, and x squared dx is 1/3 du. And of course, you could factor out that 1/3. The antiderivative of e to the u is e to the u plus c. And then, of course, the last thing we do is back substitute. If I take the derivative of this, then get a function of u, not a function of x, I want to get back to this. So I need to replace u with whatever it was in terms of x. It was x cubed, so plug that back in. And then you're here. Now, if you want, at this point, you could multiply everything by 9. I probably would, because I don't like the fractions. I like to simplify if I can. If I multiply by 9, I'll get 6 times y to the 3 halves, natural log of y, minus 4 y to the 3 halves equals 3 e to the x cubed plus 9 times c is just a different c. I'll just call that c1. And that is my implicit solution. I'm not going to verify it in this video, but if I differentiate this implicitly with respect to x, I treat y as a function of x and I take the derivative, I should be able to get back to this if I've done everything right. And this is an implicit solution to this equation. And it was actually very simple. We verified that the d was separable. We separated the variables, get all the x's on one side, the y's on the other, and then you anti-differentiate both sides with respect to whatever variable is there. This side happened to require integration by parts, and this side happened to require U-substitution. Now, at this point, I always look at my final answer and I ask myself, is it easy to solve for y? If it is, I'd like to have an explicit solution. But it's not easy to solve for y. We've got y to the 3 halves times a natural log of y here. I mean, I could use exponents to make that a y to the first, but then I'm going to have a natural log raised to a power. To get rid of logs, I could use the base e, the natural base. But then I'm going to have a guy like this, little term like this, raised to, it's going to be e to that power at some point. Yeah, it's just going to be pretty bad. It's going to be pretty messy if I wanted to solve this for y. So we're just going to call this an implicit solution of the differential equation. If I wanted to solve this for x, if I wanted to think of x as a function of y, I sure could do that pretty easily. I just divide both sides by, or subtract the constant from both sides, divide by 3, use a log to get rid of the e, and then take the cube root. And I could get an explicit solution where x depends on y. But it would be difficult to get an explicit solution where y depends on x. So we'll leave this alone. Let's do one more example. Let's go back to this one. We've already verified that this is a separable differential equation. Let's solve it. So we had dx dt minus x equals 1 plus t times x, all divided by t squared. And we said it was separable because we could add the x to the other side, and we saw that it was factorable. think I made a sign error earlier. There we go. Sorry about that. Okay, this is factorable. But I don't really need to factor it in order to get all the x's on one side and all of the t's on the other. I really just need to simplify this. I need to simplify it as much as possible. So one way that I can simplify it is I can multiply this x, and think of it as itself over 1, by t squared over t squared. And then I have a common denominator. So we'll have, and actually let's distribute this x as well. We'll have x plus xt plus x times t squared, all divided by t squared. And then let's factor out the x. And now we're here. I'd like to get all the x's on one side and all of the t's on the other, so I'll multiply both sides by t, or dt, excuse me. And I'd also like to get rid of that x that's right there. So I will divide both sides by x or multiply by 1 over x, which is the same thing. And then these guys reduce. These guys kind of reduce. We can treat them like they reduce because of the definition of the differential of x. And we end up with a 1 over x dx equals 1 plus t squared, all divided by t squared dt. Okay. So what did we do? The first thing we did was we separated the variables. And now we're here, and we anti-differentiate both sides with respect to whatever variable happens to be there. I do have a basic rule for this. The antiderivative of 1 over x is natural log of the absolute value of x plus c, but I'm going to let the constant on this side absorb the constant from this side. And then what about this one? Do you have a basic rule for that? Well, we don't have a quotient. We don't have a quotient rule, excuse me, for antiderivatives. So we've got to do something else. But one thing I noticed is that I've got multiple terms in the numerator and this monomial in the denominator. So if I want to evaluate this antiderivative, all I have to do is take each term in the numerator and divide it by that denominator. Easy breezy. And 1 over t squared is not natural log of t squared, even though it's tempting. If that exponent is anything other than a 1 there, it's not a log. You have to bring it up to the numerator, call that t to the negative 2, and then use the power rule. The algebra rule that I'm applying here is this one. If you've got 1 over x to some power, it's x to the same power, but negative. So you just bring it up to the numerator and change the sign. There are lots of reasons for that we could talk about during office hours if you want to. But yeah, that's what I'm applying here. If that n is a 1, so it's just 1 over x, you just get the log. But if that's anything other than a 1, if it's a 2, if it's a 1/2, if it's anything, then you've got to do this and then use the power rule. Now here, you're going to subtract the exponents. Here's more exponent properties. It's that exponent in the numerator minus the exponent in the denominator. Or you can think of that as one of those t's reducing. So you're going to end up with a 1 over t. I think I prefer that in this case because I don't want to think of it as t to the negative 1. I want to think of it as 1 over t because that'll give me a log. And then both t's reduce here. That doesn't reduce to 0, guys. That's a 1. I've seen students reduce that to 0. It's tempting, but it's just something divided by itself, which is 1. So now we will use the power rule here, add 1 to the exponent, divide by the new exponent. Dividing by negative 1 is the same as multiplying by negative 1, so we're good there. Then take the antiderivative of 1 over t. Antiderivative of 1 with respect to t is just t plus c. And that is our implicit solution. Now remember we started with a differential equation where x depended on t. It's implied from context that we're thinking of x as the dependent variable and we're thinking of t as the independent variable. So the variable that I would solve for here if I wanted an explicit solution is x. And I think I can solve for that. I think I'd like to do that. So rather than stopping here at this implicit solution, I think I'm just going to do a little bit of algebra and get x by itself to get the explicit solution. Now to get rid of the log, we're going to use the base e on both sides. So this is e to this power equals e to this power. Oops, that's a c. Now that constant is in the exponent because we're saying if a equals b, e to the a equals e to the b. That's what we're doing here. The entire side is up there in the exponent. Now the e and the log undo each other. They're inverse functions. So we'll have the absolute value of x equals all of this. Now there's one other exponent rule we haven't used yet. If I'm multiplying two exponents that have the same base, I just add the exponents. We can also use that backwards. Since I've got e to this power plus this, or e to this plus this plus this plus this, I can actually split that up. I can factor it. It's e to this power times e to that power times e to that power times e to that power. Okay, almost done. With this absolute value, I'm just going to drop the absolute value, put a plus or minus over here. Let's see. Then the e to the negative 1 over t, it does not simplify. This simplifies to the absolute value of t down here. E to the t doesn't simplify. E to the c doesn't simplify. That absolute value of t could be plus or minus t, so let's just call it a t. And these two guys have the same base, so I could combine them. And I'm pulling that e to the c out front for a reason, you'll see in just a moment. E to this power times e to that power, you add the exponents. And this plus or minus e to the c is just a different constant. I'm going to call that c1. All right, there's my explicit solution. X is equal to a constant times t times e to the t minus 1 over t power. This is a solution to that differential equation. So if you differentiate it, you take the derivative of this and you subtract the function itself and simplify. Turns out you're actually going to get this, which is kind of surprising. That's how we solve separable differential equations, guys. It's actually super simple. You separate the variables, you anti-differentiate both sides, and you're done. That's going to give you an implicit solution. If possible, do a little algebra to get the explicit solution. If it's not possible, just stick with the implicit solution.